This is Math 251, Section 13.5, Part B. We've now seen two different coordinate systems where we can set up triple integrals. The rectangular coordinates, x, y, and z, and then cylindrical coordinates, where two of the variables became polar, r and theta, and we kept the third variable from the rectangular system. We have one more coordinate system to look at for triple integrals. It's called the spherical coordinate system. And the first thing we need to talk about is, what do points look like in a spherical coordinate system? The first variable in the spherical coordinates is rho. And rho is the distance from the origin to the point. Notice rho is always considered to be positive between 0 and infinity. Our second variable is the variable phi. Phi is this angle with the positive z-axis. And phi is always considered to be between 0 and pi. So phi is our second variable, and it's the angle with the positive z-axis. Theta should be familiar to you, because theta is still this angle down here with respect to the positive x-axis. Theta considered to be between 0 and 2 pi. This is the most unfamiliar coordinate system that we'll face because you already had some familiarity with polar coordinates, which helped us a lot with cylindrical. This one, though, is quite new to us. So again, if our point P with coordinates rho, phi, and theta, imagine this line that runs from the origin to P. The length of that line, that distance, is rho. That line's angle with the positive z-axis is phi. And if you imagine the projection of that line down into the xy plane, the angle that makes with the positive x-axis is our theta. There are, of course, equations that allow us to transition between rectangular and spherical coordinates. And just for the amount of time we have, I'm not going to spend the time in this course trying to figure out where those came from or proving them. I'm going to go ahead and say we're going to use them, but if you're interested, I would recommend that you read in your book where they do give you the geometry of these conversion equations. We, however, are simply going to take them as givens. X, y, and z in terms of rho, phi, and theta. And then a really useful equation, x squared plus y squared plus z squared is equal to rho squared. To find phi and theta, we typically use geometry and trigonometry. We'll take a little look at that in a moment. One of the defining features that often tells me that I want to use spherical coordinates is actually the ability to use that equation. If I've got an integral that contains x squared plus y squared plus z squared, I'll typically say, hey, spherical coordinates would make that much simpler. So look at that as one of your indicators that a problem is going to require spherical coordinates. All right, we're going to start with just some conversion problems. Make sure my equations stay up here. All right, first of all, we want to take our rectangular coordinates, 3, 3, 0, and transform those to spherical coordinates. So I'm going to start by just imagining where this point is. This is actually in the xy plane, at x equal 3 and y equal 3. So it's about here. So I'm going to start with this equation to calculate rho. I would have 3 squared plus 3 squared plus 0 squared equals rho squared. 9 and 9 would be 18. And so rho is the square root of 18, or 3 square root 2. So if I were to draw the line from the origin to the point P, I know the length of that line is 3 square root 2. All right, next, phi. Oops, not rho, phi. Phi, remember, is the angle with the positive z-axis. And I'm going to do this one just by looking at it, just by inspection. If I were up here on the z-axis, and I'd like to know what angle this is that comes from the z-axis down to that pink line that I drew, that angle has to be 90 degrees. It's from the z-axis to something in the xy plane. So 90 degrees, or pi over 2. Finally, the theta, which I'm once again going to do in this problem just by inspection. Theta is the angle with the positive x-axis. So if I imagine going from the x-axis over to this pink line, since that's not a perfect diagonal, the point was 3, 3, I clearly have a 45-degree angle, or pi fourths. So this was a particularly simple problem to start with. We could do a lot of our angles just by inspection. And I'm going to say that the point then is rho, 3 square root 2, comma phi, pi over 2, comma theta, pi over 4. All right, one more conversion where maybe we don't have quite such convenient points. I'm starting with the rectangular coordinates, 1, square root 3, 2, and I would like to change to spherical coordinates. Once again, I'm going to sketch this. And so let's see, I would be at 1 square root 3 about here, and I would go up 2, so I'm going to be roughly there. I'll use my equation, x squared plus y squared plus z squared equals rho squared, to calculate rho. So squaring these, I'd have 1 plus 3 plus 4 equals rho squared. So rho squared is 8. And rho is the square root of 8, or 2 square root 2. So there, that pink line is the distance from the origin to P, and I know its length is 2 times the square root of 2. Let's get theta next. If I imagine going ahead and dropping a perpendicular down into my xy plane, theta is just this angle with the positive x-axis. So if I were to draw just the xy plane here for a moment, again, x was 1 and y was the square root of 3, then this dotted line that I drew, right there, my goal is to find theta is the angle from that line to the positive x-axis. If I go ahead and kind of finish my triangle here, what I have is a triangle with a height of the square root of 3 and a base of 1. So I do know that the tangent of theta is the square root of 3 over 1, or just the square root of 3, which means that theta is going to be pi thirds. All right, what about phi? Well, let's see if we can do a little bit more trigonometry to calculate the value of phi. I'm going to go back to drawing my three-dimensional picture one more time. And we had our point P up here. We had already figured out that that distance was 2 times the square root of 2. That was our rho. And then we had dropped a perpendicular down here to the xy plane, creating that triangle. And since the z value at this point is 2, the height here has to be 2 as well. So what I've got is a right triangle. This is a right angle here since I dropped the perpendicular. And I'm going to see if I can figure out this angle within the right triangle. It's not the angle I want. The angle is the angle with the positive z-axis, which would be out here. But it is the complement of the angle I want. So I'll be able to get what I want, the phi, from this. Since it's not yet the phi, I'm going to give it a different name. I'm just going to call it alpha for now. And I'm going to say, let's see, opposite over hypotenuse, the sine of alpha is 2 over 2 square root 2, or just 1 over the square root of 2. Using the inverse sign, that means alpha is pi over 4. Phi, the angle I really want, is the complement of that. So phi would be 90 degrees, or pi halves, minus that pi over 4, which gives me pi over 4 again. So the point that I'm looking at here is rho, 2 square root 2, phi, pi fourths, theta, pi thirds. All right, both of those examples went from rectangular coordinates to spherical coordinates. Let's look at an example where we go the other way. We'll start with the spherical coordinates and see if we can convert to rectangular coordinates. So here are my spherical coordinates. Again, this is rho, phi, and theta. And I'm just going to use the conversion formulas from the box on the previous page. X is rho sine phi cos theta. And this is actually fairly straightforward. We just plug in 2 sine pi fourths cosine pi sixths. That would be 2 times the square root of 2 over 2 times the square root of 3 over 2, or the square root of 6 over 2. Similar idea for y. I just grab the formula, rho sine phi sine theta, and plug in the values. Oops, sorry, those were both supposed to be sines this time. Again, sine of pi over 4 is the square root of 2 over 2. And the sine of pi over 6 is 1/2. So I get the square root of 2 over 2. And finally, the formula for z, rho cosine phi. So I have 2 cosine pi fourths. That's 2 times the square root of 2 over 2, or just the square root of 2. So my rectangular coordinates, x, y, z, square root 6 over 2, square root 2 over 2, square root 2. All right, so that's the basics of rectangular conversions back and forth to spherical. We'll take a look at some graphs in the next video.